So here we go. Class number 19. It's an introduction to fatigue failure. And so today's class we cover introduction to the stress life method, the SN and the SN curve. It's like the main guy that we're going to deal with. And we introduce the idea of the endurance limit and fatigue strength. So, and one of the first things I like to do is just try to make this into something that we're maybe familiar with, right? So maybe take a simple fatigue test, right? So where we're going to figure out how long is it going to take, how many bends, how many licks to the center of a Tootsie Pop, how many bends to a paper clip. So we're going to hold it pretty close and kind of bend it back and forth and bend it back and forth. I'm trying to bend it in the same place. And each one of these, each one bend back and forth is one cycle. And I've lost track. But we're bending it back and forth and bending it back and forth. And you can even feel, sometimes you feel it get hot and then boom, it gives away, right? So we've just done a fatigue test, right? Where we've bent something back and forth, and then we've applied a stress, repeated stress. That was tension and compression on each edge, each side of the thing, back and forth until. So we just did a fatigue test. Now it was not a scientific fatigue test because we didn't really measure how much force, how much moment we were placing onto there, and we can't say that we were consistent. I was consistent with the thing, with the amount that I was placing on there. But let's say we did this and we maybe were able to measure maybe how much deflection we were doing, so we could back out and we could figure out what the stress was being placed on there. It certainly was a pretty large amount because, you know, if I had let go, it would have stayed right where it was going to be. So we know we were over yield strength in terms of the amount of stress that we were applying onto there. But that's kind of like the big idea. But the big idea is that we could maybe gather that data, and we could have the amount of stress that we applied to the thing and the number of cycles until it failed, and we could create a curve, and maybe we could like predict later on, like if we did enough of these and did various stresses and did various and got various results, we'd have this data and we'd be able to go backwards through there and predict the life of the thing. So that's like the big idea, and that is the stress life method. Well, I'm going to go back up a little bit and say, well, okay, why does fatigue failure, or how does fatigue failure occur? First off, it starts with cracks, and the cracks could actually already be in. Some small itty-bitty tiny micro cracks could exist right from the day after the thing was produced. But as the loading gets applied onto this piece, those cracks open and close, those little tiny micro cracks. And at stage one, at least for mine, I say we have crack initiation, right? So that may be pretty early on where that crack. But if there's a stress riser, that's a good place for a crack to start as well. So if a stress concentration is an important place to look. And then stage two, we have these micro cracks start turning into macro cracks, micro into macro cracks. And the cracks get bigger. And these cracks are opening and closing, opening and closing, and opening and closing. And one of the consequences of this is something we call beach marks right here. You can kind of see that shows you the opening and closing, and the crack is propagating. The crack is getting larger as that crack opens and closes, right? And then stage three is this sudden failure. So that's some of the indications that something has failed in fatigue will be some of these beach marks. This is probably a pretty dramatic beach marking. They could be very, very small. We might need to look under a microscope to be able to see these beach marks, to be able to see it fail. One of the reasons why it will fail at the end is because there's actually less material there than there was before, right? So just for that the crack takes away from some of the material. So that might actually happen pretty suddenly, and the beach marks would be a very small little portion of the cross section that you might be able to look at. So I liked, for whatever reason, this is just spoke to me as a video. Let's see, not in there. Okay, I guess I must have closed it down. So let me see. I'll go to this and open it up. We'll open up this video of this piece of paper. I think it's a piece of paper. It looks like paper to me. And you can kind of see that crack initiating and opening and closing and opening and closing, and then it fails, right? Okay, so just to have like some visual representation of that, I thought was a neat thing. I also had some pictures from a shipboard. These are some documents here where we see some shipboard cracks, and my background is in ship design, and ship assessment, and that type of thing, ship structures. And you can see these got some pretty large cracks, and they usually end up happening right about where there's these transitions, and also where we have these toes of these brackets. So these are going to be stress concentrations, and you can see how these cracks can propagate. So here's like a general overview. This approach to fatigue. As the book Shigley will tell you, the stress life method is terrible. It's a terrible method of evaluating for fatigue life, but it's the most common, and it's the one that everybody learns. And so even though it's not a reliable, not highly reliable method by which to predict failure, it is the first one that everyone learns, and it's the only one I'm going to cover in class, even though there is a little bit in Shigley about the strain life method, and I think a little discussion on linear elastic fracture mechanics. These are methods that are slightly more complicated, but the stress life method is the one we're going to cover, even though it's the worst one. So just be aware of that. It's not, in terms of worst, it's just not really reliable. In fact, I think it's about 50% reliability is what we can look at, and we'll see where that comes from. The different kinds of problems that we'll do in this in this chapter are, maybe we want to find the safety factor sometimes, about compared to infinite life. We would like infinite life. That'd be a great thing. We'd like the thing to live forever. And we might find a safety factor, say how far away are we from infinite life? Like, so how far below are we in the infinite life prediction? But if it doesn't meet that infinite life, if it's being loaded higher than that infinite, that's the strength level that we would predict infinite life if we stayed under it. If it is higher than that, we want to estimate how long the thing will live. It's not a great estimate, so we got to be careful there. And we might actually want to go work backwards and design particular features for either a specific life or a specific safety factor, right? So that might be the thing that we might want to go through. So that we go to the design, we turn it backwards on itself. Or we might find some like limiting loads and say, don't go beyond this load if you want to have this criteria of maybe safety factor. So this is the big curve. This is the important one for the stress life method. This is the SN curve, where S could either be strength or it could be stress. Either way, we have it labeled as strength, but we will plug in stress numbers into here to predict the life, right? And on the x-axis, we have the number of cycles. It's important to note that this is a log-log graph. It's also important to note that for steel, we have a plateau, right? And it's kind of unique from many other materials. Not all of them have a plateau, and that plateau says that, after a certain, and these all dots represent failures, right? Failure locations. But we can see it's got this. If we could stay below this level right here, we're going to have infinite life. We're going to live forever. That's great news, right? And we call that the endurance limit, right? Or the endurance strength. SE what we describe it as. So steel has that knee right there, and it's right around 1 million cycles. Here's aluminum right here, and you can see aluminum doesn't really have that, but we might actually kind of treat it like it has like a quasi flat area. when doing some design, but we can see that steel actually has that real knee. We also want to tour this figure with a little bit more in a little more depth. Well, let's see where it comes from first. Here is just a crude schematic of this RR Moore rotating beam fatigue testing machine. So we get this data by taking a specimen, these known particular size specimen, and placing a bending moment on it and then rotating it. So the specimen, as it rotates, it sees tension and compression, and tension and compression, tension and compression. And every rotation is a cycle where it has seen both tension and compression. And we count the number of rotations, and at some point it breaks, and that break trips this thing and stops the motor, and we can see from the revolution how many revolutions we counted. So here's actually this sort of a manual diagram, the diagram from a manual of an actual machine, and I had one at the Coast Guard Academy. We had a lab where we got some specimens. First I acquired some specimens. I bought some. And I made a mistake of getting itty bitty tiny ones. I picked the smallest size, of course you would. And I picked aluminum. So, and those two things together didn't make for a very smart purchase. So when we first tried it, there it is. I think these are actually a bigger specimen. But here is the specimen inside the chucks in place. But here it is. Here's where we had these little tiny aluminum ones, right? So they were so fragile that we couldn't really even use the weight on here. We actually had to hang like a weight from the piece. Myself, I say we, myself and another instructor, as we tried to use these samples that I had bought. But it didn't take long and to have a conversation with a couple of people, and I found out there were, oh hey, we got all these samples in a drawer somewhere. So we found these actual samples. And they weren't labeled. We didn't know what kind of material they were. But we were able to estimate the ultimate strength by taking in 2015 this was, at the Coast Guard Academy. And we were able to figure out what the ultimate strength is by taking a hardness test and correlating that. And each lab group did a bunch of data as we tried a bunch of things. And you can see they actually landed on a curve, but one thing you should know is these are log graphs, so they're not as nearly as close to being on that line as they might look. But it did work. It was proof of concept of that this thing actually worked. I had let's see, Loyola Marymount had a video here where they did a little demo of that same unit. So here's that unit right there. I'll turn his voice off there. See, sorry about that. But anyway, they're showing the features of this piece, and that you adjust this weight to a particular inch-pounds bending load that you have on there. And this thing will trip right here as soon as the thing breaks. But you have a counter and a speed. So let's see. Let's go to the thing where it breaks, right? So it's rotating, and then at some point it goes kaplooey, boom, right there, and that makes all kinds of noise. So you need to have somebody nearby to turn that thing off, because you don't want to just like set it overnight and forget it, because it's going to rattle itself into pieces. But anyway, that is that's where this data comes from. That's the data that gets plotted right here, comes from test after test after test. And these specimens are polished, and you see that they try to avoid a stress concentration by making it nice and smooth transition right in here, and try not to have any surface defects. All of those things will affect, but it's a laboratory kind of environment where these are created. And so we need to see some more of the geometry of this curve and the how to use it. Right. So first off, the S prime. There's a prime that they're often using. You say, what does that prime mean? That means this is under laboratory conditions, right? And the geometry of this curve, first we start off with three really distinct points. I'm trying to make it three, right? Three distinct points. One of the points is right up here, right? And that's the ultimate strength, where it kind of makes sense. One cycle, 10 to the 0. One cycle, boom, it breaks. Well, that's the ultimate strength. Makes sense. Then we have this other point right here, which is slightly lower than the ultimate strength and should be at 1,000. And Shigley, for some reason, this curve doesn't have it at 1,000. Kind of boggles my mind. And here's the 11th edition. I want to see if the 11th edition, I haven't checked this, to see if they updated those curves. I'm guessing they didn't. But anyway, I don't mean to pick on. I love Shigley. It's a great book. I'm all about. I'm a big fan of Shigley's book. Actually, it looks like they actually did a pretty good job of finally fixing the figure. All right, so my apologies to all the people in the current editors of the Shigley book. But you could see this point right here is at 3,000. Not 3,000, at 1,000, 10 to the 3. Yeah, you go. And you can see that it's located at F times the ultimate strength. And what is F? F comes from right here. This is the fatigue strength fraction, right? And that's the thing that's defining where this knee is in the curve. And you can see that it's based on ultimate strength. Oh, and look, and they put megapascals on the top, so that's a change from the 10th edition. So that's useful too, so that you could just come back in here. And I actually curve fit this and made an equation out of it for my own use in my Excel spreadsheets. But that's kind of a nice thing. I mean, look at 120. That's an easy one to use. I like to use 120 a lot of time because then you know that you get the right number because it crosses right there. It's kind of nice. But anyway, so that's one of the one of the inflection points, the important things. So right there, and we could say that happens, that F times SUT happens at 1,000. And then we have the endurance strength, this guy SE. And initially we're going to call him SE prime, and in the next class we're going to get rid of that prime. But that prime means the laboratory environment, and that knee occurs at 1 million cycles right there. So let's take a look, and you could see they got it exact right here, 1 million, and it corresponds with SE. So over here, if we're underneath this, we're predicting infinite life. Over here, this is low cycle fatigue, and we really don't have enough. It's not as, it's hardly reliable at all for our purposes. So it's just this section right in here that we care about, and we can write an equation for it. And that equation is really sort of just a curve fit between that point and that point right there. Well, kind of. It's really just sort of a sloping thing that's taking place. Okay, and where are we going to go back to the next? We're going to go next with this. Let me see. Let me go to losing my train of thought. Boom. There's where. Oh, by the way, something to note is if your ultimate strength is below 70 ksi, you're just supposed to use 0.9. Right. So if this thing only goes to 0.9, if you're below 70, just keep using 0.9 for your F. Okay, so here is me repeating everything again. So why? That knee for steels have that knee, and it's right at 1 million cycles, and that right there is anything underneath that's the endurance limit SE, which is also, I think, of the endurance strength. Yeah, and there's infinite life. In between here, the 1,000 and a million cycles, we have finite life is predicted, and we can come up with an equation, and we can predict numerically what that life is going to be, but not very reliably, right? We don't want to like say, here is the answer, this is when that happens. And below 1,000 cycles, we call that low cycle fatigue, and we're not going to use that for predictions here. Here's some stuff that I got out of a ship structures paper. I'm not exactly sure what their full purpose was in doing this, but they made SN curves for these like structural details where you had full penetration weld, where you have like this bolted joint right here, and you can see the cloud of data that was like the point that I was trying to make when capturing this. That's the data is just all over the place, and they're drawing lines through it, right? And yeah, somebody might come up with a criteria or an equation, but you really have to appreciate the statistical nature of this stuff, especially when we first start out. We want to get an SE, right? This endurance limit or the endurance strength. And we started with an SE prime. Like, once again, the prime represents a laboratory environment, data, things that are collected in the data in the lab. So our first SE prime is 0.5 of the ultimate strength. If you take a look at this figure over here, which is pretty darn important. Let's see. Let's show a couple other figures I kind of thought were important to look at. I didn't bring up this one. I don't think I've seen him before. And here's also some data. Wow, this is also gives you sort of an idea of the statistical nature of this. You know, because that machine and the way it was run, you saw the machine, you set the stress level, or you send the bending moment onto there, which we can turn into a stress, MC over I, placed onto the thing, and you could run it a bunch of times, and you'll get a bunch of different lives. So you could see how that is true right here, and this whole thing is a curve fit through that data. It's not, you know, it's got a certain amount of unreliability, if you will, onto the thing. And you see where we're saying, okay, for our SE prime, so estimate this endurance limit, we're going to start with 0.5 of the ultimate strength for anything that's below 200 KSI, and anything that's anything above 200 KSI, we'll just use 100. So, like, where does that come from? And we have this curve right here, which is really interesting thing to check out. And it's got different materials on here, but you can kind of see that there's this slope. This is endurance strength versus tensile strength. And there's a lot of scatter here, but you could see the line that's 0.5. And then up above here, up above like 200, you can see that it kind of has a knee where it's just kind of flattening out. Kind of. But look at that, look at all that data over there. So anyway, when you say, okay, well, we'll just take 0.5 right here, that seems a little arbitrary, but it's backed up by data, albeit not super reassuring data, right? It's not, that doesn't make me all warm and fuzzy that 0.5 is like a real, like reliable, using that word again, type of deal. But that's our first thing that we calculate, is that point endurance. And in the next class, we're going to apply modifying factors to that to account for non-lab conditions. So that's going to be one of our main things to do. But now we have the curve. But let's go backwards from the curve and see what we would do to like to predict. Like, instead of using the curve and graphically doing anything, let's just apply numbers against this to estimate life, right? And it's really through that middle portion of this thing, of this curve, where we're going to predict life, right? So once again, let me go back to this curve right here. So we're talking about, first we have this region right in there. That region in the low cycle fatigue, we would say that we would use, I'm just going to go SF. I'm going to call it SF as a generic thing. It could be strength or it could be stress, right? We could stick stress in there. But we can see that it has a relationship for that curve that could be graphed using this right here, where we have the log of F divided by 3 right there. And that 3 comes from the fact that we're doing this graphing, and it's 1,000. I believe that's the reason why that we're having using that 3 right in there. Now here's the main equation that we're going to use, and that really describes this region right in there. And all it is like this equation for a line on a log-log graph, right? So here's our, you have this coefficient, this parameter A, which is going to be equal to F times the ultimate strength squared divided by SE. And then we're going to have it raised to this exponent, which is going to be B is equal to negative 1/3 log of F. Oops, I made that too close to my little equation number right there. F SUT over SE. And that can be SE prime for us for right now. Now, I caution you about the A and the B. There's a little snafu that Shigley has in there, and I don't blame them necessarily, but we have this equation right here, and here's where we have that main equation. Here's that A and that B. But not very far over, just a couple pages later, we use an A and a B. These are not the same A's and B's. All right, unfortunately. You have to be very, very careful. Do not use the A's and B's that we just calculated for here, and do not use the A's and B's that we will get from this table. That's the A and the B. This is for the surface factor, right? We're going to use those later in the modifying factors that we have. So that A and that B right here comes from here, and they get used together. They do not ever get used for this. This A and B comes from here and here, and they have nothing to do with each other whatsoever. So I think it's really important to realize that. All right, and so here is that main equation that we might want to turn this one upside down on its head. And I just noticed they changed that equation. Well, the numbers got changed a little bit too, but they use AR instead, and I want to see what they mean by AR. But usually this is rev, and it's like that's the completely reversed stress is what they mean right in there. But that's like so this is what they used to have in there, but they've decided to change. Now I say this is my class policy. When we predict life this way, this is a very rough estimate. So we want only use 2 sig figs when we get to an answer from this. If we're predicting life, I don't want to see more than 2 sig figs. I will take points off because it's implying a degree of confidence that we do not have. And if that's the case, you are in a sense lying, right? You are incorrect. You are not purposefully, but you're knowingly making a statement that would seem to imply, like if you gave me 6 sig figs, I can stand with a stopwatch, right? And I'm waiting for this thing to fail because you told me that it was going to fail at 689,742 cycles. Well, I'm going to wait for it. I'm going to count, and if it fails before then, or if it keeps going along after then, I'm going to be upset. If you you give me 2 sig figs and you said it was 680,000 cycles, okay. So it went to 900,000. All right. Oh, so it died at 450,000. I'm not so upset if compared to my 6 sig figs where you're telling me an exact amount of time. So that's my policy, and I think it's really important that we all have that kind of mindset. Another analogous thing that I have pointed out before is in the in the shipbuilding industry, we make estimates early in a design or the concept feasibility, and we throw around millions and millions of dollars, and tens of millions, hundreds of millions of dollars in how much the thing is going to cost, but we don't know. And even when we get to the detailed design, we get way over budget in things. So you don't go down and give them to the penny when you're at the early stages, or even you don't imply that you know and you have more certainty than you do. And that's that same concept right there when you're going to predict the life of something. So that was the introduction, and I'll do a couple more examples, but that was a half hour's worth of me gabbing, blah, blah, blah. But I figured I'd put this down and for posterity, and for anytime somebody was trying to catch up on a lecture that they missed. That's really my intention here. And then maybe strangers might get something out of this whole thing. So like and subscribe and leave a comment and whatever.